we spent a decent amount of time in DL talking about reflection. This is a phenomenon that you're probably familiar with from your everyday life. However, there's another thing that light can do. It's called refraction. You've probably seen examples of refraction all over the place, but you may not know it by that name. Refraction occurs whenever a light beam passes from one medium into another medium. In this example, we have air on the left-hand side of this line and water on the right-hand side of this line. Refraction occurs at the moment that the light ray passes from the air to the water. If this was a mirror, this light ray would bounce back at a 30-degree angle. However, this is water, so the light ray is able to pass through it. However, it's not going to do so unaffected. It turns out that the light ray will bend slightly as it passes from the air to the water. The equation that tells us how this bending happens is known as Snells Law. It looks like this. N is known as the index of refraction. Theta is the same as with the reflective case. We draw a line that is perpendicular to the interface of the medium. The interface is just the location where the light ray goes from traveling in one medium, in this case air, to a different medium, in this case water. So this dotted black line is our perpendicular. Let's draw one more on the other side. The angle is just measured from this perpendicular line. So for this light ray here, this angle is 30 degrees. Let's use this equation to figure out which direction this light ray will be traveling when it enters the water. N1 is the index of refraction of the air, which is just 1. And theta 1 is just the angle that the light makes when it's in the air, that's 30. N2 is the index of refraction of the water. We already have it, it's 1.33. Theta 2 is what we're trying to find, so we just leave it as a variable. Now we need to solve this equation for theta 2. The sine of 30 just so happens to be 1/2. So 1 times the sine of 30 is just 1/2. But now we have a problem. Theta is inside of the sine function, and we need to take it out. Thankfully, we don't have to try a bunch of values for theta until we find one whose sine is equal to this number. There is a function that undoes sine. It's called arcsine. You may also see it on your calculator as a sine with a little -1 where an exponent would be. Plugging that in, we get this. If I plug this into my calculator, I get that theta 2 is about 22 degrees. So let's draw what the light ray looks like when it's in the water. It's going to make a 22-degree angle with this black dotted line. As we can see, the light was bent when it passed from the air to the water. Thankfully, this equation is not too complicated, but there are some subtleties. Let's look at an example where we're going the opposite way. Instead of the light ray passing from the air to the water, it's passing from the water to the air. This time, the light ray is starting in the water and is traveling at a 60-degree angle to the perpendicular. Let's try to apply Snell's law again and see what it tells us about the direction that the light will be traveling when it leaves the water and enters the air. N1 is the index of refraction of water, and theta 1 is 60 degrees. N2 is the index of refraction of the air, it's just 1, and theta 2 is what we're trying to find. As before, we can use the inverse sine function in order to find the value for theta 2. If you plug this into your calculator, you're going to get an interesting result. It's going to say something like undefined or not a number or error or something like that. If you have a particularly advanced calculator, you might also get a complex number. but you can just take that to be an error. So what happened? Snell's law broke. When this happens, there's a phenomena known as total internal reflection. This only happens when light is trying to pass from a medium with a higher refractive index into a medium with a lower refractive index. When this happens, there is a maximum angle that the light can make with the perpendicular. If the light is traveling at a greater angle than this, it actually will not pass into the other substance. Instead, it will just reflect, hence the name total internal reflection. It's fairly easy to determine what this angle is. When light passes from a medium with a higher refractive index to a medium with a lower refractive index, it is always bent away from the perpendicular, meaning that the angle that the light is traveling is always going to increase as it passes from one medium to the other. What is the maximum angle that the light could be refracted to? It's just 90 degrees. This corresponds to the light traveling in this way and then being reflected along the surface. This surface is by definition at a 90-degree angle to this line. So in order to determine the maximum angle that the light can enter at and still manage to just barely pass through this barrier is when the angle that the light leaves at is 90 degrees. Let's write out Snell's law for this case, for this water and air example. I've also drawn in this diagram what's going on. The light is coming in at this maximum angle and then being refracted parallel to the surface. If this angle is any less, then the light ray will pass through the surface and out into the air. And if this angle is any greater, then total internal reflection will occur. Let's calculate what that angle is. The sine of 90 is just equal to 1. So this gives us, this just means that the angle is the inverse sine of this number. Let me plug it into my calculator real quick. For this case, this angle is 48.8 degrees. Again, any light ray that comes in at an angle greater than this will be totally internally reflected off the surface. And any light ray that comes in at an angle less than this will be refracted out into the air. The key point to remember is that total internal reflection only occurs when the light is passing from a substance with a higher index of refraction into a substance of a lower index of refraction. Refraction turns out to be a super useful and important phenomenon. One of the most common uses of refraction is when making lenses. Lenses work by bending light in this exact way. We'll see how all that works in a future TL.